right, how goes it? Let's run through the programming assignment and then continue talking about what goes into this. And I had already pushed this back half a week, so we're still in good shape to do this. How many people started this? Cool. All right, so we were looking at a data structure that I call the linked list, and it's implemented with an array. And the idea was we had an array like this. And instead of just storing numbers in this array, because if you want to insert something in between two elements, you have to move things around, we decided to store multiple pieces of information in here. So I have a piece of information I call data. That's where the actual number that I'm storing in my array. And another piece of information called next, which tells me the index of the next thing in my array. And when we ended a long time ago, I had posited the existence of a third column, which I'm going to call valid. And we'll play around with that in a little bit. But here's the idea. Insert the number 20. So there were two versions of this. Let me start with the first version, and then we'll go back and do it the right way. The first version was we would put the number 20 here, and we'd say there's no next piece of data. And then if you want to insert the number 30, that would go down here. We would change this thing to say the next piece of data is at index 1, and the piece of data following 30, we put a -1 to say there is no next piece of data. And then if you wanted to insert 25, we go ahead and we add that in this next empty location in our array, and we just change these pointers. We say, okay, 20 should be followed not by 30, but by 25, so we change this to a 2. And 25 should be followed by 30, so we change this to point to a 1, and then that points to a -1. And this is how we were building up our linked list. And the key is we have pairs of data. We have an actual piece of data and the location of the following piece of data. So we start with 20, that's followed by 25, that's followed by 30, and that's the last thing in the list. And the difficulty we ended with was if we insert something that should go in the beginning of the list, well, if we're always starting with this element, then we need this to become a 15. And so the way we got around that was we said index entry 0 is going to be special. This is going to be what we call a sentinel. And we're not going to care about its data. All it's going to do is point to the first thing in our list. So when we insert the 20, that would actually go here. Our sentinel would say the first thing in our list is 20, and 20 has a -1 saying there's nothing else. When we insert a 30, that goes in our next location. 20 should point to 30, and 30 is the last thing in the list. And when we insert 25, 20 now points to index entry 3, 25 points to index entry 2. And now when you want to insert a 15, we still go ahead and we put that in the next empty location, but we change this first pointer to say, okay, the first number in our list, instead of being at index 1, it's at index 4. Index 4 is 15, that's followed by index 1 is 20, followed by 25, followed by 30. So everybody cool with the idea of that? We have to talk about how to actually implement that, but that's the high-level view of what this algorithm does. All right, and then there was a question of deletion. So suppose we want to delete the 25. Well, all we have to do is note that the 20 was pointing to the 25, and 25 was pointing to 30, and just change 20 to instead skip over 25 and point to 30. So by changing this one next value to point to the 30, we remove 25 from our list. Our list now begins with 15, followed by 20, followed by 30, and that's the end of the list. The problem is, if we want to insert, I don't know, some new number, let's just insert a 40, we don't really want to put it down here, because guess what? This spot is available. Right? There's nothing using index 3 in our list right now. So this is where we'd like to put our 40. So we need a way to know that this is no longer being used. So that's what this valid column is for. So we'll set the valid column to 1 if that element is in use and the 0 otherwise. So when we deleted the 25, in addition to changing this pointer to skip over it, we would change the valid to be a 0. And now when we want to put a 40 in, what we do is we go through and we find the first invalid entry. That's right here, so we can put our 40 in here. And the last thing in the list is 30. That should point to our new entry 40. And our 40 entry is the end of the list. And now if you insert 50, again, oh, and we change that to valid. So insert 50, walk through and find the first entry where valid is 0. That tells us where to put our new entry. And then just adjust your next pointers to add that to your list.
Would we have to delete an entry? We have to go through like a number of times, right, to go back to the previous entry to have point to something new?
You need to start at the beginning of the list always, because that's the only access we have, and walk through until you find the thing you want to delete.
And then you have to go back through the list again, though, right?
You have to remember where you came from, so remember the previous entry.
You just have like a temp variable.
So have a temp variable, and always remember the number that you're looking at and the one that was pointing to that, because this is the one that you're going to have to modify. Okay, so we'll see that when we look at some pseudocode. All right, so that's the high-level view, right? All right, so let me give you details of your programming assignment. So this is PA1. So first is the definition of a node. Each of these things is what I'm calling a node. It has 3 pieces to it. It's got an actual data piece, which is an integer. It's got the index of the next thing in the list, that's an integer. And it's got a valid flag, that's an integer. So it's 3 integers. But I put them in a structure called data next and valid. And so our entire linked list is just an array of these struct nodes. So to define your linked list, you just say something like struct node list bracket 100. That's a linked list that'll hold up to 100 nodes. And that's all you're required to do for this assignment, is a list up to 100 nodes. All right, we have a magic number in here. We have this magic -1 that we're going to use not as the index of the next entry, but as a flag that says there is no next entry. This is the last thing in the list. I don't want you to put a -1 into your code. I want you to make a symbol. Define myNull uppercase -1. And when you want to use this -1, use the symbol myNull uppercase MYNULL. That's important. You could use a -1, it's going to do the same thing. You'll lose points for it though. Okay, so I want that symbol in there. We'll see why later. So set up a structure, define that symbol, and then somewhere in your main program, make this structure node list with 100 elements. That's where your linked list is going to be stored. All right, I want you to make the following functions. A function named init. It takes a pointer to a struct node. That's what an array is. So your list of 100 linked list nodes that you declared up here, your list, you could take that and pass it directly to init. And what init does is it creates an empty linked list. How do you do that? Take this first entry, mark it valid, set its next entry to myNull. That's an empty list. And then go through and mark all these other valids to be 0, so that you know all of those spots are available. Okay, that's the complete initialization routine. So initialize, make index 0 point to my null, and clear all the other valid flags. Then you write a routine called add. And add takes 2 arguments. It takes your linked list, that's the array of nodes, and it takes an integer, which is number. And you want to insert that into your linked list in order, so that your linked list is always ordered from smallest to largest. So what do? You start with node 0, you see where that points, that's your first data node, see where that points, that's your second, points to your third, and so on. Keep going through your list until you get to a number that's bigger than the number you're trying to insert. And then insert right before that spot. So you need to do some housekeeping. You need to remember where you were and where the next node is, because you want to find the 2 nodes that sandwich where you want to put your node into. Because if I want my new node to go between 40 and 50, I'm going to need to make an adjustment to node 40. I'm going to need node 40 to point to my new node, and then my new node to point to 50. So we'll see pseudocode. All right, so that's what your add routine does. And it returns an integer. If it succeeds in adding your number to the list, it returns 1. If it fails, it returns a 0. The only reason it will fail is because you don't have any space left in your array. So if you've got all 100 spots of your array filled, meaning that this valid flag is set in all 100 locations, and you try to add something, you return a fail. That's a 0. Still with me? All right, there's a print routine. Print routine just prints out the entries in your list in the order that they occur. So start at the beginning, find the first node, print out its data, find the next node, print out its data. Keep going until your next node is my null, and then you're done. So print should just print them out. I would put them on one line with spaces in between. Don't spew them out on multiple lines because it's hard to follow. All right, and the last top level routine is delete. Delete takes a linked list and a number, and it deletes that number from the linked list.
Do we need to worry about duplicates?
Assume there's no duplicates, which you can do by simply never inserting something if it's already in your list. All right, so delete, find the node, take the previous node, skip over the node you're deleting, and then clear the valid flag on the node you deleted. Okay, those are the high-level manipulations. You'll also want a search routine. So search takes the linked list and a number, and it tells you whether the number is found or not. How do you do that? Start at the beginning of the list, follow through each of your nodes. If you find your number at some point, you're done. And you can come back and return a 1 right there and say, I found a number. If you get to the end of the list where your next node is listed as my null and you haven't found your number yet, it's not in your list, return a 0. All right, so these routines, init, add, print, delete, search, those define exactly how an outside program should interact with your linked list. They do not specify how those implementations should occur. There's nothing in this definition which says what you should do when you delete a node. I've told you what to do, right? Set the valid flag to 0. But to somebody who's using these routines to work with a linked list, somebody wants to store a bunch of data and search and delete and insert using your linked list package, they don't care that you have a valid flag, they don't care that you have a next, they don't care that you have a my null equal to -1. They should never have to deal with any of those details. Okay, so this is something that we call an ADT, an abstract data type. We'll come back to this a lot. Here's a high-level view of what an ADT is. It's a data structure. It's a set of routines that you use for interacting with something without any reference to how those things are implemented. Okay, it's the interface between you and all the ugly code under the hood. Okay, it's your control panel in the car, right? You rent a car, you get in, you don't care how many cylinders it has, what kind of ignition it has, how many liters the engine is. You turn the key, you push the pedal, it goes. You turn the wheel, it steers, right? You don't care if turning the wheel is actually mechanically moving the tires or if it's sending a signal to a computer that's driving a servo somewhere. That's irrelevant to you, right? You have a fixed interface to the car. That's important because it lets you go and pick up pretty much any car and drive it. Okay, that's what we're trying to do with abstract data types. To use my linked list, to use your linked list, to use the linked list that comes with Java, I shouldn't have to understand that my null is equal to -1 and it's put in the next part of the last entry in my linked list. Right? So we're having a separation here between how do I interact with this data structure and how is that data structure implemented. Okay? This is going to be key to everything we do in Spring in 2.23. We're going to notice that everything we do is sort of up here at this abstract level. There's all kinds of stuff going on under the hood. But if we can not have to worry about those details, we're in a really powerful situation, right? We can go to any car rental agency, pick a car and drive it. That's what we're trying to do here. So the reason I'm being really specific about these routines is to try to create this interface to the user so that if I want to use your linked list code, I don't have to know that you did these things. All right, so if we go under the hood, and you have to go under the hood because you're writing this stuff, right? This is the kind of data structure that's sitting in an array of these structured nodes. And to make this work, you're going to want to write a few routines to help you. And these are not routines that the main program should ever touch. The main program should only interact with those routines on top. But those routines, when you write them, will take advantage of these two routines. The first is called getNode. And getNode basically finds an empty spot in your linked list array. How does it do that? Start at the beginning, go through, find a block with a valid entry of 0. When you get there, you know that you've got an empty spot in your array. So go ahead and set the valid flag and return that index of that free node. So getNode returns an index to an array. And release node does the opposite. If I'm deleting 50, so that I no longer care about this, I should be able to say release node, give it the linked list, give it the index 5, and it'll clear this valid flag for me.
So are we calling these in our other functions in Spring?
You'll call these inside your add and delete routines. And maybe a init. All right, so here's the detail that may not make any sense. I really want you to use these two routines inside the functions you're writing. Okay? If you've got something in your code and you decide you want to set this valid flag to 0, don't just say list bracket index dot valid equals 0. Call your release node routine. Say release node list comma 5. And the only place you're monkeying with this is inside your release node code. Similarly, when you want to get a node, don't say for I equals 0 to 100, if list bracket I dot valid equals 0, then return I, right? Put that inside your get node and only use your get node to find a free node. Okay, it'll work if you don't do that, but you lose points. Okay, and there's reasons why I want you to do this. It's because it's going to make PA2 really, really easy. Okay, you're doing all the hard work in PA1. So you should write these and write them in pieces, right? Make your structure, make an array, set up your symbol, make an init routine, and from there go to a main program. Declare your array of 100 struct nodes, call your init, make sure it doesn't seg fault or anything, and I don't know, run it in GDB. And after you call init, hit a breakpoint, and take a look at the elements in your array. And what you should see is, who cares, -1, 1, and all of these should be 0. And we don't care what's in any of these columns for entries 1 on. Okay? If that's not what your init routine does, you've got a problem with your init routine. And you want to fix that before you start trying to work with your linked list, because if it's not initialized correctly, all bets are off. So write just your init routine, go into the debugger, run it, take a look at this array, and make sure it looks the way that you want it to look. Once you've got that, make your add routine. And if you don't want to try inserting things from smallest to largest, don't. Just make your add routine add to the end of the list. Or add to the beginning of the list. That's even easier. But write your routine, run it in the debugger, add one thing to your list, hit a breakpoint, go in, look at your array, make sure it looks correct. Okay? Build it up in pieces. Don't write 500 lines of code, compile it for the first time, get 10,000 compile errors, right, and start trying to go from there. Okay? If you get compile errors at any point, the correct thing to do is not to start changing things randomly until the errors go away. Because the way that you wrote things, you wrote for a reason, right? So what you want to do is figure out, how do I write the thing that I was trying to write in a way that satisfies the compiler? Start deleting lines of code, right? Get it down to a smaller and smaller section until you've got, 2 or 3 lines of C code that's giving you a compile error. That's where your misunderstanding is, right? And then go back to your notes and figure out, how am I supposed to write this kind of statement? Okay, that's going to get you further faster than starting with 30 lines of code, which can generate, 100 error messages, and just trying to change things and hope that it stops complaining. So you're constantly doing this forward-backward dance, right? Here's where you're trying to get to, but I'll take a step here and I'll try some stuff. And it's not quite right, so I'll come over here a little bit and I'll try some other stuff. And then I'll back up and I'll go a little further and so on. So you can spend, right, a lot of time just setting this up, making a main program, just making your init routine. When that works, make your add routine. And like I say, don't be afraid to simplify your add routine. The sorting part is tricky because you have to remember where you were and put things in between. It's really easy to make an add routine that just inserts in the beginning of the list. How do you insert something in the beginning of this list? Find the next empty spot, put your data there, take this number, put it here, and change this to point down here. It's 2 or 3 operations, right? All you're doing is changing the sentinel to point to your new node, and you want your new node to point wherever the sentinel was pointing. So that now this is the first entry in the list and it points to whatever used to be the first entry. That's an insert in the beginning routine. It won't get you all the way for what you need here, but it lets you start inserting things into the list. And once you can insert things in the list, now you can make your print routine. And that's a lot of fun, because now you can throw a bunch of things in your list and print them out. And once you can print, you can start deleting, and once you can delete, you can do searches and so on and so forth. So build it up, okay? The one-day programs the rest of this week will exercise some of these pieces, which is the other reason why it's important that you do it exactly the way that it's specified in here. You should never use a malloc, you should never use a pointer, other than the fact that an array is a pointer. But you should never have to use an ampersand or a star except when you pass an array and you do a struct node star. And you should never have to use a malloc. Okay, you can do that for linked lists. If you look online for linked list code, it's all going to use mallocs. I don't want you to. Okay, I just want you to use this array of 100 entries. So far, okay? All right, let's look at your main program. So after you've got all of this stuff working, you need to bundle it into a main program. And the main program is really just, it's a little command line processor. It lets the user type in a command and it does something with your linked lists. And it should do everything it does strictly by calling those first 5 routines. The init, add, search, delete, and so on. Your main program should never go in and manipulate this stuff directly, okay? So what's your main program do? First, it initializes an empty list of 100 entries. Okay, so it's an empty list that can hold 100 things, and then print out a prompt, just a greater than sign, and wait for the user to type in a command. They'll type a command, hit enter, process the command, come back, print another prompt. They'll type a command, hit enter, process it, go back, give them another prompt. Okay, that's all your main program does. It takes a one-line command from the user, does whatever it says to do, goes back, takes another command, and continues. So your commands are the following. I can say I space 5, that says insert the number 5 into your list. If I say I space -7, that inserts the number -7 into your list. You can only insert integers, so number is any legal integer. And you should only let a node be in the list once. So if there's already a 5 in the list and I try to insert a 5, you should say node already in list. If I succeed, you should just say success. So you get a one-line message after you do this command. Either success or node already in list. If I say P, it should print the list in order on one line, numbers separated by spaces. If you say S space number, it searches for that number and prints either found or not found. D number searches for the number, and if it finds it, it deletes it and says success, otherwise it says node not found, and X just exits the program.
If I give those commands without an argument, what should I do?
Error. So anything else, print out a synopsis of the commands to show what the command should be. So if I just say I, or if I say I, ha ha ha, right, you can take that as an invalid command. Just go ahead and show me what the possible legal commands are. So make it short, like 5 or 6 line help message. So the one thing I will generally allow as far as error checking, so I is not a valid insert command. It's got to be I followed by a number. I, dog, is not a valid insert command because it should be I followed by a number. Okay, I5 is a valid insert command. If you say something like I5 ha ha ha, I'll take that as a legal command. Because it's a little trickier to make sure that you got a valid command and you didn't get anything else on the end. So don't worry about this. If you want to check that and count that as illegal, that's fine. But as long as there's a valid command in the beginning, that's all I care about. That'll make your life a fair amount easier. So if I say I5, ha ha ha, you can just take it as I5. Same thing if I say P and I put something after it, you can just take the P and do your print, and so on. All right, deliverable. So all of the above routines implemented as described, a main program as described, which will test these routines using that command line interface. Lots of comments in your code, okay? Including, for every routine, I want a comment blurb in the beginning, right, in the code before the function definition. I want the name of the function, I want what it does, what the inputs are, what the output is, what the behavior is, the side effects, everything. Okay, that goes in a little comment block right before the declaration of the function. Okay, not in the prototype, but where you're actually making the function itself. Right before that, comment block describing the function. Every function. Okay, and put it in your own words, don't copy and paste from the assignment, because it'll come out ugly, because my words are, you know. Put comments throughout your code. right? Anything that's not absolutely obvious, put a comment on. Okay, I equals I plus 1. Yeah, you're incrementing I by 1. We know that, and we know C. Why you're incrementing I by 1? What is I? Add 1 to the list size. Remember how many entries we had. Add 1 to the number of cases, something like that. Okay? Pretty much every line of your code can have a comment on it. So think about what you're doing when you write a line of C code, and if it's not absolutely clear, and in a few cases it'll be absolutely clear, but in most cases, just throw in a few words, say what it is that you're doing. And in the very beginning of your main program, I want that comment block with your name, the assignment number, the date, and the description of the assignment. Your own words, not from the PDF. So what does this program do? And these are good to do early on, right? If you have a really clear idea in your mind what this assignment is about, that's going to help you while you're trying to actually do it. And if you can't sit down and write a comment block describing what it is that you're doing, you're probably not ready to start coding it yet. You probably need to think a little more about what the overall goal is and the agenda and so on. All right, and then I want a make file that will leave me with an executable image. Okay, this has all got to be done in C. It's got to run on Linux engrcs.com, standard C, with just GCC, no extra switches. Take all of that, throw it into a tar file, upload it to Canvas. And I think the due date is a week from tomorrow now. All right, so questions about that? Questions about ODP4?
Are we assuming that there's no zeros in this array, this list?
No, you're not assuming that.
Okay. So we're inserting everything that's going to be there?
What do you mean?
So you say append, is there going to be data in this array before we start appending?
Oh, we're on ODP4, sorry. Yeah, there could be. I mean, append is just taking this structure and adding something to the end of the array, right?
Right. And will we be searching for the end of the array by finding the first zero? Is that what?
No, you've got a length argument in the structure.
Okay.
So that's what tells you how many things are actually in the array. Specifically so that we don't have to have a magic number like 0.
It does seem we're allowed to assume that that contains a valid index inside of the given array.
Yeah, you can assume the structure is valid. It's got a valid length, and everything that's in those first length entries has some meaning to someone somewhere.
So the index is offset by 1, right?
What does that mean?
Because the sentinel is at the start. They can't use that.
So we're back on PA1 now? Those last two questions were about the one-day program for.
Oh, yeah.
Yeah. So on PA1, has nothing to do with ODP4, right? So yeah, the first node is our sentinel.
Right.
And once you initialize, that should always exist, right? That should always have a my null in here and a valid bit of 1. So,
but to them, the index 0 is really index 1, right?
well, the first thing in our list would typically be at index 1. But at some point, it could be, down here if we insert it in the beginning. The other observation is we can only actually store 99 useful pieces of data in our list, because we have 100 entries, but the first one's not used for storing a data value. Any problems with that quiz from last week? It looked like lots of 5s out of 5. Okay. So let's talk about how we do some of these functions. So that's our structure. And our main program has struct node list. So that's actually an array of 100 of these things. So how do we initialize? Well, initializing is pretty straightforward. All right, list zeros, next element should be my null. To say that there's nothing after the sentinel. I would go ahead and set that valid bit to 1. You don't have to do that if you're really careful, but it's a little cleaner to leave that set to a 1. But you should never have to consult the valid bit on the sentinel, because you know the sentinel's always there. But if you don't set it to 1, you have to skip over it when you do things like search for an empty node. So I'll leave it up to you whether you want to do that or not. And then you use call release on all the remaining nodes to set the valid bit to 0. So initialization's not bad. How would we print? What would pseudocode look like for a print routine for this linked list? 95% of it is really easy. There's 5% of details that are kind of a pain.
Simple while loop, checking for my null.
Okay.
And an index that would go into the square brackets of a linked list and updating that index at the end with the next from that item.
Try it at a higher level. Let's stay away from brackets and indexes and what would be a higher level description of it?
Print out the current index and move to the next.
What's the current index mean?
Start at 0 and then have a 10. That goes the next into the 10 and then have that. That's really not good for
Start at index 0 and then
have a temp variable equal to the 0 dot next.
alright, so we got the index of the next node.
And then have a loop where you can say, well, next is not equal to my null.
And repeat all this while next is not equal to my null.
And then print it out, and then we change temp into the new next of the,
What do we print?
print with bracket temp is dot none
Here or here? Here?
below.
print list bracket temp dot data.
And then
We've got the right idea here, right? I mean, the intuition is start at the beginning, print out the first piece of data, go to the second, print that out, go to the third, and so on until we try to go to my null, and then you're done. The trick is lining it all up, right? Mainly getting it started and stopping it. And the stuff in between is fairly error-free usually. But the startup and the finish can be a little tricky.
Is there a way to get around not using temp or?
Possibly. There's always a way to get around using temps, I think. But temps are your friend usually. Variables are cheap. So, pencil and paper, forget C. Here's your list. I give this to you on a palm leaf. We're on our desert island without access to a compiler. So I scribble this on a palm leaf and I hand it to you and I say, print out the list. And you grab your charged stick and an empty palm leaf and you start trying to scribble. What's the first number you're going to write down? I don't know if this is a valid list anymore. What's the first number you're going to write down? 15. How do you know that? Because I start here, I see a 4, and there I find a 15. So it sounds like what I want to do in the beginning of my algorithm is start with element 0, see what its next value is, and print out the data piece from that element of my array. And then what are you going to print next? I'm going to print out 20 because I'm going to look at this 1 and I'm going to go up to element 1 and print out. And then I'm going to go to that element's next, which is element 2, print out its data, go to that element's next, and so on. So I need something that shows me basically where my finger is pointing. Right? My finger starts off here at 0. So finger equals 0. And the first thing I do is I change it to whatever the next piece is. So finger equals list finger dot next. So now my finger is pointing down here. So I print out that data piece. So print list bracket finger dot data. Sorry, where I start 4. So I print out the 15. And now I want to point to whatever this value is. So I change my finger to list bracket finger dot next. And now I'm exactly where I was when I got to this spot. So I can come back up here, print out the data piece, move to the next spot, and keep doing that. So this is my initialization. This is my main loop. And when do I stop? My finger points here, I print out the 40, I set my finger to 5. It points here, I print out the 50, it's a -1, I set my finger to -1. And now I know I'm done. So do this.
until dot next is my.
Yeah, so until finger equals -1.
What would happen if you did it without the third one? Like your init was part of your loop,
Mm-hmm.
and the print statement was the last thing in your loop.
Yeah, so there's some options here. This and this are exactly the same statement.
So you can get
So I could come back up here.
from the first two.
Mm-hmm. Yeah, so that's another option. Another option is to say, well, this is kind of silly. because I set finger to 0 and then I immediately changed it. So I'm just going to start off with finger equals list 0 next, and then have these two. So there's a lot of ways you can code this. Okay, so we're kind of in this nebulous space between pseudocode and C. So yeah, that's another option is put these two in a loop and leave it like that. I actually like that one a little better, I think. And somehow you need to stop this after you've gone on to the next location and it's a -1. You can do an until, you can do a while, you can do a break, you got different options. That's implementation detail. But that's a print routine, right? So that starts at the beginning. Now what happens if our list is empty? If there's nothing in the list? Finger's going to be 0, we're going to take it and set it equal to the next thing, and if the list is totally empty, this will be -1. So at this point, finger will be -1. So whatever checking we do, we need to make sure we do it before the first time we try to print. Because if our list is totally empty and we try to execute this print statement, we're going to try to index at -1.
Well, if your while is right after finger equals 0, your list next is going to be my null, so your while
Right.
condition stays.
So you could say while list finger next is not my null, and then do these statements,
You won't even have
and
to
you're
grab
done.
the next index.
Yeah, so that's a great solution. Whatever way you decide to code this, I want it to make sense to you. Okay, so what he just suggested is a really nice, succinct, clean way to put this in a few statements, right, and do your check at the beginning here. But find your own way to code it, okay, whatever makes sense to you, using this idea of how we're doing this manually, finding code that maps to that. Okay, and that's your print routine. A search routine is almost exactly the same as a print routine. To search, we basically go through this, but instead of printing, we compare the thing we're searching for to this piece of data. Right? Print it into your mind and compare it. And if they're the same number, return a 1. You don't even have to look at the rest of the list. But if we get all the way through this loop so that we come out of this while loop because we hit a -1 and we never returned, it means we never found our number. Now we return a 0. All right, so think about this. Write up some code, right? Get your basic program going. Like I say, start with an init. And once you've got an init, put an add together. If you don't want to write an add routine, just manipulate this structure by hand and synthesize a list like this and work on a print routine. Right? Just use a bunch of equal statements to make the entries in your list look like something and then see if your print routine works. And start building it up from there. All right, so go work on that, bring questions tomorrow, finish what you need for